In this video, we're going to talk about a complete system of neighborhoods for a point or at a point in a topological space. So the usual setup where X is a set and T is a topology on that set. So together that pair we'll call a topological space. And now let's let little x be an element of the set X. So in my previous video, I talked about what is a neighborhood of a point. And so here's that definition again. So recall that a subset n of x, so n is a subset of x, it's called a neighborhood of little x if there exists an open set, so O is an element of the topology, such that x is an O and O is completely contained inside of n. Got a little picture. So let's say I had the real line is my space, and let's say the usual topology. So think an interval notation, parentheses around an interval, right, when you don't include the endpoints, that's an open set. Then of course any union of those is open, and any intersection of finitely many of those is open. And let's say x is the point 3, like I have shown here. And let's just talk about what's a good neighborhood of 3. So a good neighborhood of 3 could be this closed set from 1 to 5. When I say closed, all I mean here is it's this closed interval, just like you'd say in like college algebra. So same, when I use the word closed, I mean in the college algebra sense. And so this is a good neighborhood of 3. And so to demonstrate this definition again, why is the orange set a neighborhood of 3? We should be able to find an open set that also contains 3, but is completely contained inside the orange. And there's lots of answers here. Maybe I just take the open interval from 2 to 4, where I use parentheses on the end there to demonstrate, or to indicate rather, that I don't include 2 and I don't include 4. So this little picture is just an idea of why the orange is a fine neighborhood of 3. That's old news. That's a previous video. Go watch that video on neighborhoods if this stuff's a little bit murky. What's the new thing we're going to do? We're going to talk about the set of all neighborhoods of a point. So the set of all neighborhoods of a point X is called the complete system of neighborhoods of X. And the notation that we're going to use for it is this kind of fancy n that you see down here. And then we'll put a subscript on it to indicate, well, what point are we taking neighborhoods of? So fancy n sub x. And the rest of this video is just to try to wrap our heads around what is fancy n sub x. So just to say a little bit more about it, it's a set of subsets of x. And so fancy n sub x is a subset of the power set of x, and this is one notation for that. Maybe you're more comfortable with like fancy p of x for power sets, depending on what book you like. Anyway, so it's a set of subsets of x such that, though, what kind of elements are in here? Like what kind of sets are in n sub x? Well, n is an element of n sub x if and only if, well, I want it to be a neighborhood of x. And so n is an element of n sub x if and only if there exists an open set such that x is an O and O is completely contained inside of n. So that is just exactly my definition up here of what it means for the orange n to be a neighborhood of the point. So again, all of these n's together, they all live in this fancy n sub x. Let's do an example where we compute like a complete system of neighborhoods for points in a space. So let's say that my set is just ABC, and let's say the topology on it is the empty set, the singleton A and B together, and the whole set itself. And you should always think about, all right, is that really a topology? Is this guy lying to me? Does he know what he's talking about? So you should think about why this satisfies the axioms to be a topology. So what do we want to do? We just want to write down a complete system of neighborhoods for each point in the space. So let's start with A. So what's a complete system of neighborhoods for A? And just what we're going to write down is, well, what are all the neighborhoods of A? So the first one would be A itself. And so the singleton A itself is a neighborhood of A because, well, it's open, right? And so by definition, right, I'm kind of thinking about this as n, but then simultaneously it's also acting like O in the above definition, right? So O is a subset of itself, therefore it satisfies this part, and of course A is in the singleton A. So that's a perfectly good neighborhood here. What else? AB, great, that's for the same reason, right? So in this case, again, this can kind of act as n and O in the above definition up here. And do we get anything else? AC also is one, and what I want you to notice here, right, and we talked about in the previous video, neighborhoods don't necessarily have to be open. So why is this a good neighborhood of A? To demonstrate that this is a neighborhood of A, it's because, well, A is an element of T, and so A is in that, so in other words, this is my O. So A is an O, and that's completely contained in AC. So that demonstrates why AC is a good neighborhood here. And let's see, I got to get rid of some of that stuff now. And the last thing, though, is that the whole set itself is a good neighborhood of A. So this would be a complete system of neighborhoods of A. You could try to think about if there's any more, but I think you'll find that there aren't. Let's talk about a complete system of neighborhoods for B. And so, well, A comma B, that set is a good neighborhood of B. And again, in this case, if I think about for the context that this is N, right? What is the open set that N contains that also contains B? Well, it's self, right? So it gets to function as both because it's open. But then are there any other ones, right? Well, there's nobody else. There's no other open sets besides X itself that even contain B. So the only other neighborhood of B is the whole space itself. So since there's no other open sets that contain B, we're all finished there. And let's find a complete system of neighborhoods for C. And so again, you're thinking about, okay, what are the neighborhoods of C? And again, it's not just the subsets of X that have C in it. You've got to have subsets of X that have C in it, but that also contain an open set that have C in it. And if you look through this, if you look through your topology, what are your open sets? Well, X is the only set in here that contains C. And so that is going to be the only neighborhood of C.